how many benefits does Mark have? What would you do? I would use the same aggregator right here. Now, I say per request, but I still have that data. Darn, that's a select count. This is a select count. And so since I have the same data, I'm going to expose a second endpoint to say, well, since I already have that data, I'm not going to complicate my infrastructure by this. And so it depends on how much data. When do Mark's benefits expire? Well, now we're starting to build a whole subsystem here. And so in that case, probably not. Searching. Searching. How do you do searching here? Somebody upstairs there talked about indexing. You know, when we started talking about the name and kind of database replication. If I pump out indexes, now I can have a search aggregator here that does searching to give me back all the keys, which then can go to the specific microservice and get the data. And so there's a lot of possibilities for this aggregator. How do you do reporting in microservices? It's called the data pump, and that would be exactly the same pattern right here. Yes, we are duplicating the data. Okay, so one of the consequences of this pattern, and the question was, well, what about the consistency here? Yes, so the caveat here is this. We are duplicating data. We are aggregating or doing a map reduce or a filter of this data. Do I have all the data? There's two things. Caveat. One, highly reliable, highly available, persistent, guaranteed delivery messaging. And so I'm going to make sure that that's a persisted queue and that I have guaranteed delivery so that if I get a success that I've written to that queue, when the aggregator comes up next, let's say the aggregator fails. When it comes up, it has state, and it's going to read all those messages that it didn't get. However, if I want to be sure, I can actually do something called a checksum algorithm or a checksum pattern. And that is where I know that I have 100 of these. Every time I send out a message, I stream out to Kafka a request ID saying, I just sent this out. And I can do a checksum, basically, pattern to be able, when I gather all those metrics, do I have the same data that I sent? And so that's another way to harden that, yeah. But yeah, it does, the caveat is highly reliable messaging. Again, we start dealing with trade-offs. Is this a perfect solution? No. Does it fit within microservices? No. Is it a Band-Aid? Yes. So, here's the point. Do you remember our list that we're adding? Remember that list? So what are the things that we should look at as we're analyzing our environment in microservices? Too much inter-service communication. Boom! Number 2, too many shared libraries. Boom! Number 3, how many orchestrators do you have? That's number 3. The number of orchestrators. Number 4, the number of aggregators. These are Band-Aids. Microservices was never meant to do this. But when we try to apply it in the real world, we have to. However, too many of these is a great indicator right here that this is not the right architecture style for us. And maybe we should roll back to a service-based architecture where we have common data and large coarse-grained services. You know, we try to say, but we need high agility. We need all this testability. It will never work anyway, because these are all the, and I can't remember what we titled this. These are all the things to check. What was the title we put on this list? The metrics. Yes, the analysis metrics. That's what it was. So this is going to call this the analysis metrics. Fantastic. Okay, good. Yeah. Oh, yeah.
We can have like get name kind of a customer aggregator.
Yes.
Order aggregator and that kind of thing.
No.
Similar
No,
types.
I wouldn't. And so the question is, well, with the customer and like the name, couldn't I have like a name aggregator? And no, I would not use the aggregator pattern for that. It's too much data. I'm truly then duplicating data. So you can kind of see the difference between these patterns. Orchestration has no state. because I'm getting all customer data, which is a lot of data. Can you imagine if I aggregated every bit of customer data together? Then I'm truly duplicating my entire ecosystem. So it's a great comment, a great question, because it points to when you would use each of these patterns. What if we aggregate only the name? Here's the point. I aggregate the name. How do I get the name? I still have to go to another microservice. So I might as well go to the source. Yeah, I mean, these are good. I love this, though, because now we're brainstorming. And we're saying, well, what about this? And we're realizing, I'm not solving the real problem. Because, yes, I'm storing the name and the ID relationship, but rather that would be better for caching. Yes, which I want to get to next.
So on the same line, so if the benefit aggregator requires number of benefit for mark, or get name requires only name.
Right.
So when we take the data from different services, we only take name. So as we add more calls there in the aggregator, we can add more in the queue, something like that. Let's say, for example, if you need...
We could, yes, yeah. Although what I would generally do is if I had more information to aggregate, I probably would do different state. I would have a different service with a different request. And the reason why I did the number was because I had the same data. Like the expiry. Now I have to expand my schema, and suddenly the service is getting a little bit too big and full of information. That's where I might start saying, I don't know. Whether I would say, well, I've got a crossroads now. Do I create another aggregator or not? So yeah, that's... but let me show you one last adapter, because I do want to get onto caching, because we do only have a half an hour left. But let me show you the service gateway pattern. So here we have microservices. We've got an API. We have protocol-aware heterogeneous interoperability. Remember that. Protocol-aware, because we don't have an ESB. We're not doing protocol transformation anywhere. So how in the world, if I got a proxy or a gateway that's communicating to all my services with REST, thumbs up there, but I've got a custom payment system in the mainframe that uses old ISAM files, which communicates to the world through the mainframe's native protocol for ISAM, which is OTMA. How in the world do I communicate with that with a protocol-aware system? Well, you got it. You know now. It's called a microservices gateway. So let's drop another individual, separately deployed microservice called a gateway. And that gateway communicates to the rest of the world through REST, but it knows it has that protocol transformation to know how to convert a RESTful call to an OTMA call to COBOL to be able to get to this payment system and get the information and come back out. Okay. What I generally use for especially the gateways, but also the orchestrators and gateways, I generally use Apache Camel, regardless of my platform, because I can create it. I can get any sort of Docker image for Apache Camel. Camel is an open source ESB, a mediator, but it's just a jar file. It doesn't have a server, and so it's usually embedded. It requires a server, but I don't need a server. I have a microservice. In 7 lines of code, I can orchestrate. In 4 lines of code, I can get to OTMA. Camel C equals new camel. And this is what my code would look like in Java. Camel C equals new camel. C.start. I've just started camel. My route extends route builder. Public void configure. Open squiggle. From REST address dot to OTMA IIOP 435, which is the port / name refund. Bingo. Oh, and close squiggle. There we go. 7 lines of code. I've just communicated with the mainframe. Yeah, I love Camel for that. Yes.
Gateway can be horizontally scaled, I agree, but you won't be able to horizontally scale mainframe. You'll be hit by, let's say, number of connections to mainframe and all that.
That is correct. So scalability is going to be an issue, isn't it? Because I am limited to the number of connections to the mainframe. How do I solve that problem? Well, let's say I have 20 operations in my custom payment system. I've got make a refund, make a credit, do a partial refund, do a partial payment, do a full payment, do a partial credit. 20 operations in this payment system. We already know this is old COBOL code using ISAM that we're going to convert over to Java. What I would do is this. I would take those 20 operations, And I've confirmed we're going to move those eventually over to Java. I'm going to create 20 microservice gateways. Each of these gateways right here is going to front each of those payment operations. So instead of having one gateway called payment, no, I'm going to have a gateway microservice called refund, another one called partial payment, another one called full payment, partial payment, full refund, credit check, all the operations. And now, you know what I've done? I've created a placeholder in my ecosystem, communicating to all of you through REST. Doesn't scale, does it? However, watch this. Now I take that COBOL code for partial payment. I write it in Java in this gateway, and then I move the database fields over, or create a new database. Now, this gateway becomes a functional service, and no one even knew about it. The clients don't know about it because that's the endpoint right there. So that's how I can start to get the scalability, is to now start it's converting. It's a migration pattern of architecture. And so, I love these gateways for that reason. All right, so we have an endpoint on each of these, which would be 20 of them in that case. And each of these are either dedicated to a specific system or an operation in a system. And so this is a way of actually creating the placeholders for a large conversion effort in microservices. And so they're pretty cool. One of the questions here that I wanted to address, I think we're getting there. We've only got 20 minutes, and I want to do caching. Integration logic. Okay. So this is all really good for communicating between services, but what if we have a large ecosystem in a bank or insurance company or retail shop, or I've got all these systems right here, and I'm starting to use microservices, and so I've got all these microservices we're defining, but I've still got other systems. And the problem is these systems need to talk to microservices. How do you integrate microservices into an environment as we start to move towards this level of modularity? Okay, that was one of the questions or concerns that we had from this morning. All right, well, how in the world do we do this? Notice we've got an ESB here, by the way, because this is our large enterprise system. There's an ESB tying everything together, which is good. But do we want to tie all these microservices to an ESB? No, these services really aren't hiding or floating in the ether. This is what it looks like. Instead, those services are well-defined into domains. They're called application domains fronted by a gateway or an API. So look at what we have here. This is one that you might want to look at later afterwards because I know this is really small. So this is our policy API. This is our quoting API. There's our issuer, and there's our claims API, for example, in insurance. Now, all those systems need to talk to those services. Here's what happens. They go through the integration hub because I have no idea what protocol these are talking on. ATMI, OTMA, RMI, .NET remoting, all that kind of stuff. So now the integration hub makes RESTful calls to the API. Now you can start to see when we start to create microservices ecosystems and how do we integrate the rest of those into our regular systems. What I want you to think about is that bounded context, because each of these domains right here, here's a domain, domain number 2, domain number 3, are all self-contained hidden units. It's a share nothing architecture style. And so the key point here is this. I'm not going to share these services. They're exposed through these APIs, but don't you dare go into any of those. Now, let's assume that System B needs to orchestrate these 6 services. Well, should that orchestration be here in the gateway? Because there's 6 endpoints here. Shouldn't that kind of just say, well, go here, then here, and we'll put that orchestration code in the gateway? Or, I'm sorry, in the integration hub? No. Watch this. I know this is going to be small, but watch this. You see these 6 services right here? That's what I need to integrate for that call. You know what I do? Move those down a little bit, and I'm going to create an orchestrator microservice. And now there's a single call from the ESB to the API. And then this orchestrator microservice orchestrates these 6 and then comes back to a single call into the ESB, which does the protocol transformation and contract decoupling over to System B. That is the bounded context. What you want to be careful about when you start integrating microservices in this orchestration is where to put that orchestration. That would be a big mistake to put it here, because now I've bound each of these service endpoints to an orchestration level there. Yeah, that's why those orchestrators are also so powerful, because I have no idea what other systems are going to call me. Okay, so that's the way we would actually integrate those. Are the orchestrations asynchronous? No. Oh, right down here. Oh, yes, hopefully so. Yeah, but that could be a messaging call, a RESTful call, but generally the point is, if I'm broadcasting, then yes. If I need a response, then no. Yeah, it wouldn't be. Whoops, yeah, I didn't catch the first part.
I'm just suppose I'm opening an Amazon product page of a mobile or a television, and then I'm seeing some cross sell and upsell and then comments, and there are different parts and sections of it. Definitely they will be orchestrating every part of it and then providing the data. But
Right.
what I see is I keep on getting the data, as you said. One gets I was not seeing it and then I got it back and it was available. So I'm just trying to understand whether the statefulness of when the request was made and when it got back. So how this whole statefulness is maintained by orchestration layer, because are we maintaining that state by API layer or?
No, the state, and that's the point, is that the state would be maintained. Each of these microservices has its own data. And that's where the data is, and that's why I need to orchestrate those six, because I need all six of that information. And that's what I'm saying. That state, so this is orchestration, so this is not aggregation. But the point is the state of the data is actually down here. The request is system B needs all that information that you just described. And so the point is, but that's now been divided up into microservices. So system B makes a single call into the integration hub to say, get all that information for me. And now the integration hub says, well, that's been converted to microservices, but I know that there's an endpoint in the API. Let me invoke that endpoint to say, get all that information, get all page information. And that's where it goes to this orchestrator microservice, which says, get all page information. And it has the code to orchestrate these six with all the data. So the state really, orchestration doesn't really have state. But that aggregation is passed all the way back up. So we only have 15 minutes left, and I really want to show you the caching piece, because that's something that is really, really, really hard to do. And what I want to show you is a really cool thing about how can you actually share data. How can you do data synchronization? And this gets a little bit complicated. So it usually takes an hour and a half to go through this section, and we have 15 minutes. So let me show you. This leverages a combination of something called microservices and also something called space-based architecture. Space-based architecture gets its name not from the cloud, but rather data science or a computer science term called tuple space. Tuple space is multiple parallel processors sharing the same memory address. And so the point is, when we talk about architecture, what that means is caching. There's no database, which gives me near infinite scalability. And let me show you how this pattern works. So this is a microservice in a space-based topology. As a matter of fact, if you want to get more information about space-based, you can actually go to Neil and I's videos on O'Reilly. Also, I have a book that's free called Software Architecture Patterns. And I describe space-based in that as well. But let me actually show you the deep dive part of space-based. So that will give you kind of a general view of this architecture pattern. But this square right here is a separate physical node. And in that physical node is the virtual machine. And these services are in a container in that virtual machine. Here's a customer information service, and then here's a wish list service. And let me show you what this looks like. That code, this is my deployment unit. It's a microservice. It's in a container. And what it has is all of my class files, and then an in-memory data grid, a cache, along with its replication engine if I'm using replicated caching. This would be something I would download, Hazelcast. It could be Apache Ignite. It could be Coherence. It could be Gemfire, those sort of things. And so here's the point. What we want to achieve here in this pattern of caching, and I'm going to show you the most complex pattern, and then I'm going to show you the differences between distributed and replicated cache. But let me show you this pattern right here. So what I have in order to make this work, and this is a merging of two architecture patterns. We're taking microservices and space-based architecture, and we're putting them together to answer these questions. How can I have several thousand microservices and share the single 4 terabyte Oracle RAC relational database cluster? How can I have all my microservices in the cloud and my data on-prem? How can I significantly increase the performance of my microservices? All three of those I'm going to show you. So in order to make this pattern actually work, what we want to do is we don't have a database. Oh, it exists, but we don't want to be able to read that data. So what I'm going to do is I'm going to have a separate, now there's, let's say, 2 or 3 instances here, 2 or 3 instances there of this other wish list service. Here's another instance, multiple instances, but this is on a separate physical node, and that's important, and let me show you why. Because here's our database. Oh, we have it. It's on-prem or it's somewhere. It's a large Oracle RAC relational database cluster. It's a single schema, whatever. Okay, so watch this. What happens is I've got a data writer that does this. Now watch, I just updated some data. I just changed the name. There we go, a name update. That was pretty fast. Let me show you. So watch the sparkle occur. Are you ready? Okay, here we go. Watch over here on the left-hand side. I update the name. So watch this. It goes into that microservice. I just updated the name. Now what I do is instantly replicate that name across all other instances and across all other nodes of that microservice, that customer demographic service. Hazelcast, Ignite, all the tools do that. Okay, so now what I have to do, though, is I've got a database down here. And so what I have is something called a data writer. And this is a microservice. It could be a separate system. It could be something like a data hub, like Ab Initio, for example. But what happens is I send a data pump. Again, here we have a data pump. I send an asynchronous fire and forget message of that new name. Customer 123's name is actually now William, not Mark. Okay, and that's just a fire and forget, asynchronous messaging, very fast. Now the data writer, notice, picked that up and now updated the central data store to say, oh, customer 123's name is actually William. Okay, that's how that works. Now watch what happens. This instance here, there's all the data for the customer. This whole entire cluster, boom, goes down. Ooh, all those instances went down on that physical node. Uh-oh, now I got to read the data. No, I don't, because watch what happens. Those instances come up. Let's say I'm just using Coherence or Gemfire. So Gemfire says, oh, I need to load you. And it loads it from an existing instance. That's why I have them on separate physical nodes. Because if a node goes down, I never, ever have to read the data. Because I always have an instance available that has the data to replicate to you. And that is really fast. We're talking about 100 milliseconds to replicate that data. So can you see, this pattern requires, if I just lumped all these clusters on the same physical node, the chances are that I have to read it. And watch what happens. As a matter of fact, let's demonstrate that. All of a sudden, boom, here we go, ready? There it goes. That instance went down. Oh, that's no problem because I've got more instances here that can replicate the data. I know I had a major failure. Very first thing I'm going to do here, very first thing, I'm going to create a third physical node and put instances there. Because you can see in the space-based architecture pattern, when we merge microservices, I don't want this to happen because now there's no data up there in the cloud or on-prem. There's no data in the cache. Now I have to start up and read it. So watch what happens. I start up an instance. Now I've got a data reader as well. This is another microservice or a group of microservices or a separate system or, like I said, a data hub. So now watch this. This is where all my SQL is, by the way. And so here's the point. I start up, the first instance that starts up does a hazelcast.lock. And so now I'm going to use Hazelcast and say lock. And when I do a lock, every instance that comes up, Hazelcast client is going to try to replicate. And it says, but the cache is locked. I do a lock, and then I specify the cache name. Now, I'm locking the cache because I was the first instant up. Now watch what I have to do. I have to make a request to that data reader. And now the data reader sends me all the information. Notice I just loaded up the cache. I do a hazelcast.unlock cache name, and now, boom, everything gets replicated, and I'm ready to go. I want to try to avoid this like the plague. And so that's why if I do have this occurrence, which would be rare, I would further guarantee it by adding a third physical node with multiple instances there to make sure that I really guarantee I don't have to read, because this is slow. Okay. This pattern looks great until, what if somebody updates this database? You know, this is why caching's hard. Let's actually go through that scenario. Let's say that we have an external application that does an update to the data that I have in the cache, up in the cloud, or in my microservices, even on-prem. It doesn't matter, cloud or non-prem. This has a lot of special cases. By the way, because this is all in-memory data, this is so blinding fast. It's really fast. So now, somebody asked about data volumes as well. I'm going to do multiple questions at the same time with that. So what I need is a data updater. Now, I can either use a wiretap, which means intercept that call, or reroute all updates to something called a data updater. This could also be, again, ab initio, for example, is a great implementation of this. Or it could be a microservice. But the point is, this external application can talk to the database, but maybe I use a trigger, which goes to the data updater. But the point is, the data updater knows that data is being updated. Watch this. Data is updated, and what it does is it publishes or sends it to a queue, and this ended up getting it. So I send that data up to a queue. That happened really fast. And now the name is updated here, and of course now it's replicated to every single instance across every physical node. That's how this pattern of architecture works. Now you see what I've actually done here with this pattern. Isn't it interesting? What do I have? I have three components. I have a data reader, I have a data writer, and I have a data updater. You know what it's doing? It's actually surrounding that database, isn't it? Can I have several thousand microservices all talking to the same exact database? Yes, I can. It's the merging of these two patterns. Data volumes, that's a 4 terabyte database. Why microservices work so well with this is because separately deployed, single purpose. I do not have 4 terabytes in these caches. That's the customer info. There's the wish list. Here's the preferences. Here's the payment information. In other words, it's a small enough chunk of that 4 terabytes of data that it makes this possible. So data volumes doesn't matter as much. This is transactional data. This is on-prem. These are all in the cloud. It's a way of doing database synchronization as well, increasing the performance. It's a really neat pattern. But you know what else I can do? Is now I can version database changes. Because do I actually talk to the database here? No. I have a cache, which is a separate contract than the actual schema. I can now make schema changes, and I just want to make sure I have this here. Good, I do. So because of these data writers, readers, and updaters, I can now actually do transformations, because what is that? That's an actual object, or it's XML, or it's JSON. And I can version that. So I can make a database change, and now I can do transformation. There's my change to a schema. Broke it. I broke a schema change across 2,000 services. That's okay, because with these data hubs, or these services, wrapping this, what I can now do is transformation logic in every one of these points. That's what the T is here, transformation. So everybody's using .1.4.3 of that particular contract for that schema. And now over time, what I can do is change that version to match that schema change, and I can do this incrementally. Yeah, so anyways, let me hold off on the questions for a little bit, because I know we're out of time, and I really want to show you one more thing, which is the replicated versus distributed cache. Just in case you all have to leave, here's what I want to do. Because I'm getting all excited because there's so much information. But I know you probably have a lot of questions and stuff. If you do have to leave, because we're almost at the end anyway, here's a couple of places. I'm going to come back to that, but just in case. If you go to my website, developer2architect.com, there's the lessons menu item right there anyway. This is a place you can always get hold of me. If you go to the Contact Me, it goes directly to my email. And so please feel free to go there for any questions that you maybe didn't get. Absolutely use me as a resource, because you can also go to my website directly, wmrichards.com. As a matter of fact, a lot of my publications are I put them on Developer to Architect, but 100% of them, including all the messaging and stuff, are under publications here. And like I said, I've got a lot of books, and most of them are free. The software architecture patterns, the microservices books are free. You can download those. If you've got a Safari Online account, you have pretty much everything I've ever published, which is about 17 books and videos. But the other place you can go is exactly to, if you go to my website, I also have a Contact Me here. It goes directly to my email. So you can absolutely say, hey, I was in your deep dive class, just had another question I wasn't able to ask about this. And I usually try to respond within a day or so. I know I'm not going to be able, with this kind of a crowd, I thought we did a pretty good job, though, of getting the collaboration and the questions and stuff. And I know you have hundreds. I'm not closing the class now, just in case you have to go. But I know you probably have hundreds of questions remaining. Please don't hesitate to email me and just say, hey, I was in your deep dive training. Can I ask you one more question regarding this? And like I said, I've been doing a lot of travel, but I try to get back at least within a day. And so those are just some sources you can always get back to me. But let me show you one more thing before we go. And because it's something I did allude to that was important for me to show you. And that's the fact that right here, this is the whole products list that you can use for all this caching stuff. Apache Ignite, Couchbase, EHCache, Encache over in .NET. Redis is great in the .NET world because Azure actually has a Redis hook already in there. I really like Redis for a cache because it has a great backing database. Hazelcast is another one that there's so many products right here. How in the world would I choose? Let me show you 3 more slides and then we can go. First, should I use a distributed or a replicated cache? Let me show you the difference and how to decide. A distributed cache means this. Here's all my services right here. It doesn't have to be microservices. These are macro. It doesn't really matter. The point is a distributed cache says, I have an external cache, Hazelcast. I'm just going to use that as an example. Hazelcast, and there is the cache right there. If I want to get to it, I have a Hazelcast client library, which has a protocol to get to that cache very quickly. This is usually a proprietary protocol. Each product has its own wire level protocol to be able to connect to the cache. This is not a RESTful call. It's very, very quick. So it's fairly low latency, but it's still making an external call to this cache right here. So here I get not so great performance because I'm having to go out to get the data because it's not in memory for me, but the consistency is sky high. What I do have, though, is a single point of failure, don't I? If Hazelcast goes down, I'm out of luck, which means I have to cluster this right here or mirror that cache on another node. And so I've got some reliability. I should put a reliability arrow. I got to make sure I mention that. A reliability also goes down in terms of the availability, not reliability. Availability goes down. And let me show you a replicated cache. Replicated cache looks like this. The cache is actually in my JVM. It's in heap. It's actually part of my Docker image. And so the point is I still have a client library, Hazelcast. And what it's doing is it is communicating through the proprietary protocols between each of these client libraries right here. And so now that's when we saw it makes a change and it replicates it everywhere. Here I've got incredible performance. The memory or the data is right in my or it's in heap. It's right there. However, consistency might be a little lower. Okay, so that's the difference. Almost all, not everyone, almost all of these products support either mode. I can do replicated or distributed. Well, Mark, which should I use? Let's end with this slide. Which should I use right here? Hold on one second. Which should I use? So, replicated or distributed? Let me give you some guidelines of what I use to determine which one would be most.